Hello everyone. Today inshallah we will continue our lectures. I will start a new chapter which is dot, cross, scalar and triple multiplication. In the previous lecture we already finished eigenvalues and the eigenvectors. We used them to diagonalize a matrix. We defined the algebraic multiplicity, the geometric multiplicity, the condition for a matrix to be on the diagonal form or in a diagonalization, how to get the eigenspace. Okay, it's really very important to go through them and to try to resolve them these problems. It's very, very important. So I need you to go through them with writing or resolving these problems. It's very, very important. Today we are going to go through chapter 7, which is the dot, cross, and scalar triple multiplication. It's a chapter that contains a lot of information that will be needed in analytic geometry down the road. Also, it will make re-evaluation for the steps that we had previously in eigenvalue and eigenvectors in order to check the orthogonality between vectors and so on. So this is really a very nice chapter. Okay, let's start. I will start with some definitions about the dot multiplication. The dot or the Euclidean inner product, sometimes we call it inner product, sometimes we call it the dot product or the Euclidean inner product. It's simply if you have two vectors and you want to multiply them, I will multiply the components, okay, of each vector of the two vectors in each other. So it will be A1 times B1, A2 times B2, A3 times B3. That's what we call inner product. By the idea, one of the symbolization for this multiplication between vector, I can write them U dot V. Usually in the standard books, we usually dot. So multiplying U dot V, it means an inner product between these two vectors. We call it the dot product. Simply, you will multiply the corresponding elements of the components starting from the first plus the second plus the third component. So it's really a very nice, very easy to do step. Okay, throughout we shall consider the vector space R3, which is equipped with the Euclidean inner product. So U dot V is equal to V dot U. If you replace them, it will make no difference because you are simply replacing, instead of A1, B1, it's going to be B1, A1, the B2, A2, and the B3, A3, it will make no difference. Also, I can distribute the addition between two vectors on the dot multiplication, as you can see. Multiplying by a scalar, it will be the same exactly as making the inner product first, then multiplying by this scalar. U times U should be greater than or equal to 0. It will be 0 only if U is equal to 0, and it makes sense. Okay. Once more, we need to define the norm or the magnitude. Or Ziyad, if you remember in the previous lecture, we used the magnitude or the norm in order to get a unit vector while we were getting the P matrix required for the diagonalization. Do you remember? Getting the eigenvectors, we already divided on their norms. The norm of a vector, it is the square root of the sum of the squares of its components. معايا مش So it's very, very simple. All I have to do, A1 square, A2 square, A3 square under the square root, that's the magnitude of U. Okay, Farid, if I want to get a unit vector from any vector, all I have to do is to divide the components of this vector on its magnitude. So all I will have to do is to divide A1 by the magnitude of U, A2 by the magnitude of U, A3 by the magnitude of U. Then the magnitude of the unit vector is going to be just only a unit. Hold on. So it's really very simple, and as I told you, the magnitude is very equal to 1. Okay, these two inequalities or these two statements are really very important. So we will need them in calculus 2 down the road, and we will depend on them in plenty of proofs. He's stating for you that U be a vector R3 and alpha be a real number. then the magnitude of u is greater than or equal to 0, which makes sense. Only 0 if u is equal to 0. Alpha u is equal to the absolute of the scalar value times the magnitude of alpha. This relation, I will depend on it in some proofs. Also, this will leave us with the Cauchy-Schwarz inequality, which states that for the inner product of u dot v, so getting the absolute value of u dot v, it should be less than or equal the magnitude of u times magnitude of v. Also, it makes very common sense that if you have u plus v and you're getting the norm, it's going to be less than or equal the norm of u separate plus the norm of v separate. Of course, the norm is the square root of the sum of the squares of the components of the vector or the sum of these vectors. Are you with me? So, mainly, these two remarks, either Cauchy-Schwarz inequality, which states that the inner product, the absolute value of an inner product between two vectors, because it's going to be a number, is less than or equal to the magnitude of each vector when you multiply them together. So it's from now on, we will use it as statement, as a theory, as truth. And also for this inequality, it's very, very important. Now, according to Cauchy-Schwarz inequality, if u and v are non-zero vectors in R3, let's introduce the notation of the angle between two vectors. The angle between two vectors, it's really very important to evaluate, to find an angle between two vectors. And it's really very simple, related to the inner product between these two vectors divided by the magnitude of each vector. So simply, if I have two vectors and I need to find the angle between them, I will multiply them in inner product, then I will divide on the magnitude of each one of them. That's the cosine of the angle between u and v. Which means the angle between u and v is equal to cosine minus 1, this value. So this value should be less than or equal to 1 because it's a cosine for an angle. Okay, which means u dot v by this value, which is the cosine of the angle, less than or equal to 1, greater than or equal to negative 1, which makes complete sense. These results are the peak of the cosine value. So, if you have cosine theta, if you remember, this is the value of the cosine. So the maximum value is going to be a positive 1. The minimum value is going to be negative 1. This is for cosine of some alpha. So it makes sense that the inner product by the magnitude of the two vectors, which is cosine the angle between these two vectors, is less than or equal to 1, greater than or equal to negative 1. Which means the angle will move between 0 and the pi. The corresponding angles between 1 and the negative 1. It will be between 0 and the pi. And that's the statement, that the angle is between greater than or equal to 0 and less than or equal to pi. Also, if the cosine is equal to 0, if the cosine is equal to 0, it means that the angle is going to be pi over 2, which is called, in this case, we call them perpendicular vectors. So that's another condition for perpendicularity between vectors. And it makes sense when this value is equal to 0. If you have this value is equal to 0, it means the denominator is equal to 0. Am I right? Then, once more, for this fraction to equal to 0, it means the denominator will equal to 0. And this completes, and this is acceptable, and it makes sense, because in the previous lecture we also stated, if you have two vectors and you evaluate the inner product between them and the result is 0, it means these two vectors are perpendicular, okay? So, now I have the cosine angle, as I told you, and the consequence of both of them. Under the assumptions of previous definition, the following holds. The angle between u and v is, of course, equal to the angle between v and u. And the dot product is also equal to the magnitude of u times the magnitude of v times cosine u, or the cosine, the angle between these two vectors. All I did is just making a cross multiplication for the main relation, then we'll be able to get this relation. Okay, for example, if you have these two vectors, which are the standard or the canonical parts of the canonical vectors in R3, I have 1, 0, 0, and 0, 0, and 1. The angle between them is, the angle between these two vectors is 90. Am I right? 90. From where did you know that the angle is 90? Because if you get the inner product between these two vectors, you will have 0 times 1, 0, 0 times 0, 0, 1 times 0, 0, and the sum of them is equal to 0. Am I right? If you want to have the angle, okay, between the vector u and the vector v, it's going to be really very simple. U dot v divided by the magnitude of u times the magnitude of v, which is going to be 1, 0, 0, dot 0, 0, 1 divided by the magnitude of this vector, which is simply root for 1 square, so it's going to be 1 plus times the square root of 0, 0, and then 1 to the power of 2, which is equal to 1, so the result will be 0. Am I right? Say that. Are you with me? Makes sense? Okay, very good. So these two vectors, if you have these two vectors and you want to evaluate the dot multiplication or the angle between them, you will multiply these two vectors together, dividing by the magnitude of each one of them, which will lead to 0. That's pi over 2, which is 90. If the dot product is 0, you have an orthogonal vector. We call it perpendicular vectors, as you will see. How to check if you have linearly dependent vectors? How to check? Also based on the results of the inner product. Okay? So this paragraph shows you that if you have u and v linearly dependent non-zero vectors in R3, since u and v are linearly dependent non-zero vectors, then for alpha belongs to R without 0, you will have u is a multiple of v, and that's the dependency. What's the dependency between vectors? Regardless of the inner product or the multiplication, you can find the vector from another vector by multiplying in certain value. مش ده linear combination? Do you remember؟ معايا فريد؟ ما هو ده معنى dependent، ان انت تقدر to generate a vector from another vector by multiplying in certain constants. If I have just only one vector and this vector depend on it, I can generate this one by multiplying the elements in a constant. If this vector can be formed from two vectors, I will do the linear combination, multiplying the first vector in alpha 1 plus multiplying the second vector in alpha 2. So it makes sense. Okay? So therefore, the angle between u and v is 0 or pi. So if you have vectors dependent, then the angle between them is going to be between 0 and pi. So if I have u times v, which is alpha v times v, so I'm multiplying a vector in itself, you will end up having alpha over absolute or the magnitude of alpha, which is going to leave you with 1 or negative 1. 1 if it is greater than or equal to 0, or negative 1 if alpha is less than 0. That's the condition for the dependency. If I have a vector and I want to see if it is linear combination or something, all I have to do is to do this check. Okay, u dot v is equal to the inverse of 1, which is 0, and the r positive negative 1, which is pi. That's the angle between them, 0 and pi. Orthogonal vector means if you have u and v and perpendicular vectors, the multiplication is equal to 0, as I told you. And also you will have u plus v to the power of 2 equal to u squared plus v squared, because they are perpendicular. And this is similar to Pythagorean theory. If you have two vectors and you are getting the sum of them, once more, if I have two vectors, that's u, that's v, that's the addition of these two vectors. So, and this angle is a right angle, so it makes sense. So you will have this relation. The magnitude of the sum of them is equal to the magnitude of the first vector plus the magnitude of the second vector. So that's the orthogonal probability. Mainly, he is giving you an equivalent ways to find an orthogonality between two vectors. Okay, let's go through this step by step. Let B belongs to n, which is a number, integer, and for a sequence of vectors, u1 up to ub, those vectors belongs to R3. So u1 up to ub is an orthogonal set or orthogonal set of vectors if multiplying ui times ug, the result is equal to 0. What we mean about this statement or this subparagraph? It's like the vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. Those three vectors form a three orthogonal vectors. So any of them, if you multiply, the result will be 0. If you multiply 1, 0, 0, and 0, 1, 0, so try to do the dot multiplication, the result will be 0. If you get the first with the third, the first with the second with the third, all of them are going to equal to 0. So it's an orthogonal set of vectors. So Jana, I can call it an orthogonal basis for R3, which is the standard basis for R3. I can also check if there is another basis for R3 or rather than the standard basis. And if this vectors or the vectors of this basis are perpendicular or not. فاتن تفهموا لي؟ طب قولوا لي كده تاني. You know that R3 ممكن يبقى لها أكتر من basis صح؟ طيب البيزس دي بيبقى how many vectors in it؟ 3, 2, more than that. Okay? طيب ال 3 vectors دول هم basis for a certain vector space. If they are orthogonal, any two of them, if you multiply them together in an inner product, okay, the result will be origin. ده اللي هو بيستيقظ. برضو أنا أقدر أخليهم orthonormal. إيه الفرق يا فريد between orthogonal و orthonormal? So like, what's the difference between orthogonal and orthonormal? Huh? Normal, it means the magnitude is equal to 1. So orthogonal and orthonormal, or orthogonality, orthonormality, both of them means these vectors are orthogonal. Okay? But in orthonormal, the magnitude of these vectors is equal to 1. But orthogonality, it's a general case. Okay? So once more, if I have u1 up to ub, they are orthogonal vectors. How to check if they are orthogonal? Multiply each two of them. The result will be 0. Okay, for the orthonormal, if you multiply them together, you will be in just only two situations. If you multiply the vector in itself, the result will be 1. If you multiply the vector in any other vector, the result will be 0, because they are perpendicular. Do you read me? It's exactly like 1, 0, 0. 0, 1, 0, 0, 0, 1. Those three vectors are orthogonal and also are orthonormal. Orthogonal because any two of them, if you multiply, the result will be. And orthonormal because if you get the magnitude of each one of them, the result will be 1. Okay? So once more, the sequence u1 up to ub is said to be orthonormal, or u1 ub are said to be orthonormal vectors if u1 to ub are orthogonal and unit vectors. And then the multiplication of ui dot ug, if I is equal to g, so they are the same vector multiplying by itself, the result will be 1. If I doesn't equal to g, they will be different vectors, and their multiplication will be 0. Okay? So now I know what's an orthogonal set of vectors, what's an orthonormal set of vectors. How to get a normal vector from a general vector. How to do it? Divide the components on the magnitude. Divide the components on the magnitude. Okay? Okay. تعالوا بص على دي كده. Let beta E1, E2, E3. So it's the standard basis or whatever basis. Okay? Be an orthonormal basis for R3. Stop. What's the orthonormal basis? So E1, E2, E3 like 1, 0, 0, 0, 1, 0, 0, 0, 1. They are orthogonal and their magnitudes 1. Okay. and I have a vector, I have a certain vector u, which can be written as a linear combination, صح? Based on this basis. So it's going to be alpha 1, E1, alpha 2, E2, alpha 3, E3. If I have another vector belongs to this vector space, so it can be written as beta 1, eta 1, beta 2, eta 2, B3, eta 3, where Miss Nada, beta 1, beta 2, beta 3 are بسميهم ايه؟ coordinates صح؟ مش دول coordinates؟ طيب والفا 1 الفا 2 الفا 3 اسمهم ايه برضه؟ coordinates of vector u with respect to basis beta صح؟ Okay, so once more the coordinate sequence of u with respect to beta, the coordinate sequence of v with respect to v, ادي الثلاثه اللي هم الفا 1 الفا 2 الفا 3. Those are beta 1, beta 2, beta 3. Okay? If I multiply u by v, it's exactly like multiplying alpha 1 times beta 1, alpha 2 times beta 2, alpha 3 times beta 3. Because simply the components of the vector are the coordinates of the vector. Please, don't skip any piece of information. I need it all to be in your mind. I'm not saying something new here. I'm stating that the vector 4, 5, and 6 is exactly like 4 times 1, 0, 0, plus 5 times 0, 1, 0, plus 6 times 0, 0, 1. Are you with me? This is why the vector by itself with its components, it's exactly like the coordinates in the canonical form. Okay? So once you multiply these two vectors together, if I'm multiplying these two vectors together, it is like multiplying the coordinates with respect to this basis times the coordinates of this vector with respect to this basis. So the multiplication, the inner product is actually can be look at it as it was like multiplying the coordinates in each other. Do you read me?
And then do I multiply them by beta?
Mm-hmm.
Do I multiply them by beta?
By what?
Beta, like E1, E2, E3.
Yes, it's going to be exactly the same. But if you multiply E1 in itself, the result will be 1.
I know after I got like the multiplication, they took away the x, I multiplied by.
No, خلاص, it's done. You have the value. Okay? Okay. Also, the magnitude of u is the sum of the squares of the coordinates. This is mainly because E1, E2, E3 is the canonical basis. He's giving you this slide as an introduction. If I give you another basis other than this one. But he's starting with you with the canonical basis, which makes a complete sense. It's very, very simple and it's very easy to evaluate. Okay? So once more, that's the magnitude of V. Remark also that the coordinate of the first component is simply evaluated from multiplying u by E1. This is alpha 1. And if you multiply alpha 2, it's exactly like multiplying u by E2. Why? Because if you multiply u, yes, by E2, which is 0, 1, 0, so it will eliminate the first two coordinates and there will remain just only alpha 2. And this is exactly the same. Also, introducing this remark for you here in order to generalize it on another basis down the road. Okay, are you with me? So now, these are the coordinates of u, b with respect to orthogonal basis. Now I can write u. Those are the coordinates. Now I can write u once more as the coordinate, which is alpha 1 times. So I will replace alpha 1 by this guy, which is going to be u times E1 times E1, u times E2 times E2, u dot E3 times E3. Now I'm introducing, this is really very important. This is slide explains that the dot multiplication of a vector with respect to orthonormal basis, orthonormal basis for this vector space. It's exactly like multiplying the various coordinates. This is number one. Also, I can get the coordinates. How to get the coordinates? It's simply, I will multiply the vector that you need, its coordinate, dot the first vector in the orthonormal basis. This is going to be alpha 1. Then multiplying the vector that you want times E2, which is the second vector in the orthonormal basis, and so on. He made this example for you because it makes sense, since you already know that's the orthonormal basis for R3, for example, is 1, 0, 0, 0, 1, 0, 0, 0, 1. So it's already in front of your eyes. It's very simple to deal with. Okay? Let me see this example. Okay, close. This slide is okay? Okay, now, wait. Let's go through this because your questions probably will be answered in this slide. So once more, before going to this problem, once more, I have vector, which can be a linear combination from this basis. That's another vector, which can be also a linear combination from this basis. The difference between them will be the difference in the coordinates. So, multiplying the inner product, or getting the inner product, it's like multiplying the coordinates. Okay? Now I know how to get the coordinates. I'm going to multiply the vector times my vector times the first vector in the basis. I will get the first coordinate. I will multiply the vector on the second vector in the basis. I will get the second coordinate, and so on. So I can get the coordinates alpha 1, alpha 2, alpha 3. And I can generate this U from any basis of this vector space by multiplying the coordinate times the vector, as we already know did previously. Now, look to this example. It's really very important. First of all, Miss Nada, if the first vector, normal vector, is it a unit vector? The first vector, is it a unit vector? R of Z, I will have to get, yes, the magnitude. Bring me the magnitude of the first vector. So it's going to be 2 over root 5. صح؟ معايا الجنة؟ It's this vector is simply 2 over root 5. Huh? 1 over, and that's U1. It's a unit vector. Why it's a unit vector? Get the magnitude of U1, which is simply a square root for these, the square of these components. The square of the first component will be 4 over plus 1 over plus a 0, which is going to come up to 5 over 5 under the square root, which is, so already it's a unit vector. This one too is a unit vector. Yes. Negative 1 squared is positive 1. 2 squared is a 4. Add them together, it's a 5. Over 5. So it's a unit vector. And that one too is a unit vector. That's the first check. So all of them are unit vectors. Am I right? Are they orthogonal? Are they orthogonal? You have 3 vectors. Do they form an orthogonal set? زياد. أعمل إيه عشان أعرف إذا كان orthogonal set ولا لا؟ Multiply them in each other, each 2 by 2. So if I multiply the first vector times the second vector, let's say that 2 times negative 1, negative 2 plus 1 times 2, the sum is 0. 0 times 0 is 0. So U1 is perpendicular orthogonal on U2. Perpendicular means orthogonal. Multiply U2 by U3. Multiply. Negative 1 times 0, 0. 2 times 0, 0. 0 times 1, so U2 is orthogonal to U3. What's remaining? U3 and U1, let's do it. 0, 0, 0. So already this basis, which is U1, U2, and U3, are orthonormal basis or orthonormal set of vectors. Am I right? Their multiplication 2 by 2 is 0, which means they are orthogonal. And the value of the magnitude of each one of them is equal to 1. Okay, very good. So support the following vectors in R3. Check that U1, U2, U3 is an orthonormal basis for R3. They are orthonormal basis for R3. First of all, orthogonal. Number 2, they are unit vectors. And they are independent on each other. Am I right? Yes. So number 1, U dot V is equal to 0. Given a vector ABC, I want to see if they can generate any vector in R3. How many vectors? Mainly, there are 3 of them, and we are talking about R3. So the dimensions is okay, is already set. So they can generate any vector. What's the shape of any vector in R3? A, B, C. Okay? A component in X, a component in Y, a component in Z. They will be able to generate it. Here we go. That's the component, general component for V, A, B, C, belongs to R3. Let us determine the component of V. I need to determine the components of V with respect to U1, U2, U3, which means I will need the coordinates of this vector with respect to this basis. Am I right? Okay, I will do it. Coordinate sequence of V. Do you still remember the coordinate sequence that I told you about? Alpha U times E1 and so on. I will do it right now. Now I will try to get the coordinates. Remember, alpha 1 is U dot E1. Here is U is ABC. And the E1 is the first vector. Now for the second coordinate, يا فريق هتبقى ازاي؟ U is the vector ABC. And the E2 is going to be the second vector. Do you read me? And for the third coordinate, it will be exactly like multiplying the vector ABC, okay, in E3. What's E3? Which is using 1. I will do it with you step by step. So it's a V times U1 and V dot U2 and V dot U3. Just multiplying them together, you will get 2A plus B over root 5, negative A plus 2B over root 5, and C, which are the coordinates of this vector with respect to this basis. Of course, this value is really very simple to grab. بص كده. Multiply this vector times that vector. So you will multiply the first element or the first component by the first component. So it's gonna be 2 over A over root 5, then plus. Multiply the second, which is B, times 1 over root 5. So it's going to be B over root 5, which is simply 2A plus B over root 5. That's the first component, exactly the second and the third. Any questions? What's stated here once more? If I have an orthonormal set of vectors as a basis for a vector space, I can get the coordinates of the vectors in this vector space according to this relation by multiplying U times E1, U times E2. So multiplying the vector by the elements of the basis of this vector space. ماشي? Okay? Any questions? لا خوف يا موضوع. Okay. Now U1 up to UB is a orthogonal sequence of non-zero in R3. Then U1 is a sequence of linearly independent vectors. So if you have those vectors and they are orthogonal, okay, then they are linearly independent. Both of them together. So if you have vectors and they are orthogonal, so they will be independent vectors from now on. Okay. Consider the following vectors, which are 2, 1, 0, negative 2, 4, and 0, and U3, 0, 0, 2. The sequence U1, U2, U3 is orthogonal. Yes, I can check that they are orthogonal. If you multiply any two of them, that is absolutely 0. It is already multiplied in front of you. U1.U2, U1.U3, U2.U3. Also, since U1 up to U3 is an orthogonal sequence of 1 zeros, we have U1 up to U3 as linearly independent. U1 up to U3, they perform a basis for R3. So if I checked the orthogonality, it means I have linearly independent set of vectors. They will form, if they have the same dimension, then they will form a basis for this vector space. Okay, since U1, U2 is an orthogonal basis for R3, and the magnitude of each one of them, this is the magnitude, is going to be 4, 2 squared, which is equal to 4. 1 squared is equal to 1, the sum of them is under the square root, is going to be a root 5, so I can get orthonormal set. So orthogonal, it means orthonormal, because the difference between them is to divide by the magnitude of these vectors. Are you with me? Okay. Another thing, some problems, like the 1, 0, 0, 0, 1, 0, 0, but some bases, I'm sorry, the magnitude will be 1, will equal to each other. Like 1, 0, 0, 0, 1, 0, 0, 0, 1, the magnitude of the three vectors is 1. Also, in the previous problem, in the previous slide, the magnitude for the first vector was root 5. For the second vector is root 5. The third vector was 1. So, here for this set of vectors, this one, and that one, which are perpendicular on each other, and the magnitudes are different. The magnitude of this one is 5, but the magnitude of this one is 20. So, and the magnitude of this one is 2. It will make no difference. I divide each one of them on its magnitude. So the first vector will be divided by root of 5. The second vector will be divided by root of 12 because it's magnitude. And the last vector will be divided by 2 because the 2 is its magnitude. Okay? This is how to get an orthonormal set of vectors out of